everybody. Glad you could all make it. I'm Matt Wood. I'm our host for our wonderful series. Thanks for coming back. I hope you all had a nice holiday break. Welcome to 2011. Dr. Dan Batcheldor will be giving our first talk of the spring. Thank you for the music. And Dr. Batcheldor got his bachelor's and Ph.D. from the University of Hertfordshire it's not Shire, he tells me. Got his Ph.D. in 2004. He's just a young guy. From 2005 to 2009, he was at the Rochester Institute of Technology, where he started as a postdoctoral fellow and was, after that, a research scientist, assistant, and associate research scientist. He joined us just about 1 year ago. He is an assistant professor. He is also the director of the Olin Observatory. Was rugby, but now he's a family man and working hard, so doesn't want to give blood that way anymore. So, without further ado, Dan will be talking about astronomy 2010 to 2020. Thank you, Dan.
Thank you, Matt. So this isn't the first time I've given one of these public lectures. The last time I gave one, I thought, you know what, I'm going to put the word black hole in the title and see what happens. And it was standing room only. This time I've put a boring title that probably means nothing to most of you. And now I know who the hardcore really are. So thank you all for coming, despite a seemingly boring title. So thank you. After the last talk I gave, Dr. Wood came up to me, he thanked me, and he said, yes, we all enjoyed your talk. Thank you very much. But you kind of left the audience with a feeling like everything that you've been trying to do with black holes, there's nothing else that can be achieved. So you gave this lovely talk about black holes and what we know and what we've done in the past couple of years. But in the next 10 years, you said, well, there's nothing that can be done. So when Dr. Wood asked me to give another public lecture talk, graciously said, thank you very much, yes, absolutely. And then I started scratching my head about, well, what am I actually going to talk about? And I remember back to Dr. Wood saying, you idiot, last time everybody left going, there's nothing left to do in astronomy. So I thought I'd give you a talk about, actually, though, there's quite a lot left to do in astronomy. So this talk might actually be a bit different to the talks you're used to. I'm not going to specifically talk about a highly technical research project. I'm actually going to review a document that came out at the beginning of 2010 that the astronomy community refers to as the Decadal Survey. The Decadal Survey was actually done by the entire community of astronomy and astrophysics. So everything that you're about to see in this talk is the opinion of the entire astronomy and astrophysics community, including amateurs, including professionals, including educators. Okay? Now, this document was collapsed down into a 325-page, very concise document called New Worlds and New Horizons. And the title is very apt, as hopefully you will see soon. The picture on the front is a star-forming region in M17. It's actually a Spitzer image, so what you're looking at is infrared data using the MIPS and IRAC camera. I always like to kind of explain where data comes from or pictures come from when I put them up on slides rather than just going, pretty picture. But we'll get back to that in a minute. So, what am I actually going to talk about? Well, when I was asked to give this talk, it was actually 2010, so I thought, I'll call it Astronomy 2010 to 2020. It's actually 2011 now, so what I'll first do is review what happened in 2010. Then we will get on to the questions that perhaps many people in the audience would like to know about. How much money does astronomy in the United States have? What are we going to spend it on? Why should we spend it in the first place? Who got to decide how we spent that money? And then, what big questions are we hoping to answer in the next 10 years? And then, finally, the driest part of the talk will be an endless list of recommendations of what the astronomy community should be aiming to do over the next 10 years. Okay, so, question 1. What were the astronomy highlights of 2010? This is by no means a complete list of everything that happened in 2010. These are just a selection of some of the highlights to show how broad amount of science is actually being done in the astronomy and astrophysics community. So first of all, Hubble's undiscovered country of primordial galaxies. At the beginning of the year, we started to use the new cameras that were installed on the Hubble Space Telescope for the first time after the fourth servicing mission. Well, technically the fifth servicing mission, but the fourth named servicing mission. So what we can almost see here is a picture of the ultra-deep field done with one of the new cameras on board the Hubble Space Telescope, WIF-C3. This camera is a lot more sensitive than the previous cameras, and we've actually been able to start to pick out galaxies. I promise we've been able to start to pick out galaxies at an age of 13 billion years. So this is only 700 million years thereabouts after the universe was, after the beginning of the universe, after the Big Bang. This one came out at the beginning of the year. Earlier this week, there was yet another press release to do with similar data, that they found yet another galaxy that's slightly even further away, 13.2 billion years away, light years away. So because of this refurbishment of the Hubble Space Telescope, we've been getting a lot of new science from the Hubble Space Telescope itself. You upgrade the cameras, you increase its sensitivity, and every time you increase your sensitivity in astronomy, you find new things that you were not necessarily expecting in the past. Now, I do love to talk about myself, galaxies and quasars and black holes, but there is more to astronomy than that. And one of the most interesting solar system observations that was made earlier last year, beg your pardon, was of a comet-like object spotted from the ground that was then later followed up with, you've guessed it, the Hubble Space Telescope. And this comet-like object, when viewed through the Hubble Space Telescope, actually turned out to be very unusual. Instead of the nucleus of the so-called comet being in the center of the coma, it turned out that the nucleus was actually outside of the coma itself. So this is actually evidence of a past collision between asteroids in the solar system. So this stuff here is actually the dust left over from the collision of two asteroids. And this is the first time this kind of data has actually been seen. We thought that perhaps there were collisions between asteroids, but this is the actual first time that we've actually seen evidence that there has been collisions between asteroids itself. So we've gone from the absolute farthest distance away in the universe to just in our backyard. But wait, there's more. People tend to forget that we have been roving around Mars for 5 years. And unfortunately, at the beginning of 2010, one of the Mars rovers, Spirit, actually stopped transmitting. It had been stuck in the sand for quite some time. What you're looking at is a picture of Mars. You can see that one wheel of the rover is over here. It's been kind of seized, stuck for quite a while, and it's been dragging itself through the sand. But this wheel over here quite clearly shows that this rover is stuck. And because it's not been able to maneuver itself to clear off its solar panels, it's now lost energy, possibly, and is no longer communicating with us. But this rover's lifetime was 90 Mars days. They call them sols, 90 sols. And in fact, it lasted over 2,200 days on Mars before it got to this point. So this is a remarkable achievement. It was HST's 20th birthday. When HST was launched, I was 12 years old. When I was 12 years old, my imagination was running wild. We were being shown pictures like this regularly. The Hubble Space Telescope is one of the reasons I became an astronomer, because I looked at pictures like this and I didn't just say, wow, cool, like looking at a picture of a fighter aircraft or something. I actually went, wow, cool, what is that? I want to know what this is. Okay? So Hubble is now 20 years old, and I've kind of grown up with it myself. And it's been a remarkable achievement getting the telescope to even last this long in the first place. There was a second rover on Mars, Opportunity. This rover is still operational. There is a rover that was designed to last 90 days on Mars, 90 sols on Mars. It is now past 2,490 days working on Mars. And the type of data that comes back from these rovers is astounding. It is easy to forget, much like during the Hubble, during the Apollo missions that we were regularly going to the moon. It is easy to forget that there are people on this planet that go to work every day on Mars, taking photographs like this of a crater that's half a mile across, Victoria Crater. It's sometimes easy to forget exactly how much science is being done in astronomy, just in 1 year. So where is opportunity right now? Well, you can actually see opportunity from one of the satellites that's orbiting the planet in support of the rover missions. Right now it's on the edge of a 100-foot crater called Santa Maria. It's sitting right there. Well, it was at the end of the year. You can just about make it out. And it has actually been trekking across the surface of Mars now for nearly 2,500 Mars days. It actually started up here. It landed in a crater up here and then wandered down to Victoria Crater, which is this crater here. So this crater is the picture you just saw, the picture we just panned across. And it's now gone down to Santa Maria Crater, which is just here. And it's still going strong. So the plan is to send it on to this huge crater here, Crater Endurance, which is about 14 miles across. They're going to take the long way, so they're going to come down here. So there's another 14-mile trek for this little rover planned, and hopefully it's going to keep going strong. So those were some of the highlights of 2010. So now I can get on to the big questions, right? You're all taxpayers. Well, most of you are taxpayers. So how much money is there to spend? How much of your federal dollars are we going to spend on astronomy and astrophysics? Okay. So, first of all, the NASA astrophysics budget. Now, you have to take these numbers with a pinch of salt because there's all sorts of economics that go into them that, quite frankly, I don't fully understand. These are 2010 federal year dollars, so with inflation they'll change. But there are just about $400 million per year to spend on astrophysics in the NASA budget. Of the total NASA budget, that's less than 0.33% of the total NASA budget. The National Science Foundation has about $250 million per year to spend on astronomy. That's also less than 0.33% of the total NSF budget. And then, believe it or not, the Department of Energy also puts money into astronomy through high-energy physics. And they have about $20 million to spend per year. And that's, as you can imagine, a tiny fraction of the total Department of Energy budget. Okay? How does this rack up in terms of the total federal budget? How much of the total federal budget are we going to spend on astronomy per year? So, your illustrious Barack Obama has requested $3.69 trillion for the 2011 federal budget. This graphic you're seeing here was produced by the New York Times. It sectionalizes each part of that budget and puts it into, for example, Social Security. For example, national defense. For example, paying the interest on the national deficit. I'm not kidding. Right? What else have we got? Medicare. Right? So these are actually these squares here are proportionally part of the $3.69 trillion that each of your taxpayer dollars are going on. So science is down here. Now it's broken up into several different parts. This box down here on the left is NASA, the entire NASA science budget. So not astronomy and astrophysics, right? Astronomy and astrophysics is 0.33% of this. This is the NSF total budget. Okay, where astronomy has 0.33% of that. Okay, and then I think this one here is the Department of Energy. Okay, So in terms of the total amount of your tax dollars that are being spent on astronomy, if this screen has a resolution of, let's say, 1,048 pixels this way and 760 pixels this way, how many pixels do you reckon you get? 1. 1 pixel. Astronomy and astrophysics, as part of the federal budget, is 1/5,000% of the total federal budget. Okay, so why should we spend this money in the first place? It's not seemingly that much money, but let's, make sure that we've got a good reason to spend it, right? So I'm kind of preaching to the choir here. You've already turned up to a boring titled talk in the first place. So clearly you are going to know why I'm going to go through the following slides. Okay, so you already know that astronomy stirs the public imagination because you are the public, and my title stirred your imagination, right? But astronomy also brings together the human spirit better than any politician can, without any words. And I go back to the pictures coming from the Hubble Space Telescope, and I was never told to become an astronomer. I just looked at pictures like this, and I read the caption underneath saying stellar nursery, or whatever it said. And I read that caption and I went, wait, stellar nursery, so stars are born? Does that mean they die? How do they evolve? And you kind of run through these questions. As I said, I'm preaching to the choir. So you all are thinking these questions or have all thought these kind of questions in the past. I want to understand this. I don't just think it's cool. I want to understand this. And this is the difference between astronomy and some of the other areas that people can take careers in. Right? Astronomy gathers people in. It doesn't just put up cool pictures. It asks questions. Why is this like this? Why do we see it this way? And there are better demonstrations of how astronomy stirs the human spirit. This is a picture from Apollo 8, orbiting the moon. Very famous picture, Earthrise. And what does this picture say? Without, any politician at all. This picture is showing you that we are on a fragile planet, and we are one small speck in the tiny, tiny universe around us. And there are no political boundaries here. There's no delineation because of your background. There's nothing that says that you will be disadvantaged because you have you're some part of some minority. Pictures like this bring together the human spirit. And the real problem is that corporations know it. They know it. You may not notice, or you may notice and it just glosses over you, but there are corporations out there that are playing on your love of astronomy every day. How do I know that? Well, every day I get hungry. So perhaps I'll want a galaxy bar. Perhaps I'll want some sun-made raisins. Perhaps I'll go see my grandmother and get some half-moon cookies. Perhaps I'll have some starbursts. But this isn't the only set of corporations. It's not just food. Right? After you've had a bag of sun chips, your breath is awful. So you need some gum. What if you're still hungry? Good question. Well, then you go to a car manufacturer and you say, I want to buy a car so I can go to the store to get more food. And then perhaps you don't like these car manufacturers. So perhaps there are other car manufacturers out there that even name their cars after astronomical objects. What have we got here? We've got Taurus, Eclipse. Okay, it's the undergraduates right now. Can any undergraduates get this one? Nova. It's a Chevy Nova. Yeah, this one's the Ford Galaxy. This one? It's a Pulsar. It's a Nissan Pulsar. Yeah. So let me get this straight. You've gone and eaten You've been influenced by the corporations to go and eat their food, chew their gum, drive their cars, then go see their movies. How many of the top 100 blockbuster movies are based on, and I use the word based in the loosest possible sense, based on astronomy and astrophysics? Some of them are better than others. My wife is petrified of E.T. She's sitting down there. What if you don't like any of these movies? And, I wouldn't blame you on, well, most of them, with the exclusion of Star Trek, of course. Well, if you don't like the movie, then you can go home and you can watch your TV shows. How many TV shows can you name that are based on astronomy and astrophysics? And again, I say based in the loosest sense of the term. And if you don't like science fiction, well, you can watch programs about science fact-ish. Science fact-ish. There are whole channels now devoted basically to astronomy and astrophysics. Okay? So you might not even realize it, but you can spend your whole day being surrounded by the influence of astronomy and astrophysics. Okay? That is a powerful medium for this world to embrace. But there's more. Astronomy is not just about the fact that we love astronomy. Astronomy engages a huge number of people, whether they are professional astronomers or not. And what we mean by this is astronomy is an accessible science. You don't have to be in a profession, you don't have to be a professional astronomer to do astronomy. There is a huge and vibrant amateur astronomy community. The general public are greatly interested, as I've already pointed out, with astronomy. And to be quite honest, us professionals know this. And we are using you guys in a very boring and mean way. We are getting you to do our work because you love doing it. The Galaxy Zoo. There is a huge database of galaxies. Computers aren't very good at classifying galaxies. Humans are. So let's just put up pictures of galaxies and get humans to go, that's a spiral galaxy. The Galaxy Zoo does that. SETI at home invades your computer, uses your CPUs to start processing the signals that the SETI project, the Search for Extraterrestrial Intelligence, has got in its database. Einstein at home is yet another invasion of your CPU. It's voluntary invasion. It's not like they're terrorists or anything. But Einstein at home is using all of the signals from LIGO and other gravitational wave observatories to search for the first signals for gravitational waves. And then some of you may or may not be aware that most astronomy databases, most of the professional astronomy databases, are available to the public. You can right now lift up your laptop and go and download data directly from the Hubble Space Telescope. As long as the scientist who asked for that data in the first place has been given a year, has been given this proprietary period, after that year, the data is public. You can go ahead and use it. You can go ahead and get it yourself. Okay? What else? Astronomy brings together many, many fields. Okay? My illustrious boss likes to say that physics, when you're doing physics, you're just doing chemistry, you're just doing biology, you're just doing all of this other stuff, just in another way. Okay? But when you're doing astronomy, you don't even realize it. But you are doing geology, biology, chemistry, computer science, just to deal with the data that you have, just to model the data that you have. You are dealing with high-performance computing. There are telescopes now mounted in aeroplanes. There are spacecraft that fly that are telescopes. You have to learn about aeronautical, mechanical, electrical, and optical engineering. And of course, stars. They're a huge nuclear fusion furnace. When you do astronomy, if you're an astronomy major, you are learning about nuclear physics and particle physics. So it's not just like you're going out there and looking at the sky and drawing pretty pictures. You may not realize it, but you are doing all of this. So astronomy brings together many, many different fields. So there is a huge problem, not just in America right now, throughout most of the world, in that young people are not interested in science, technology, engineering, and mathematics. There is a STEM crisis, okay? The number of people actually wanting to get involved with science and technology is declining. But astronomy, as you've already seen, is a magnet to these STEM disciplines. Just because you want to do astronomy, just because you are an astronomy major, doesn't mean that you necessarily are going to end up being a professional astronomer. In fact, less than 75% of astronomy graduates actually go into academia. It is unusual for somebody to stay all the way through astronomy or stay all the way through physics and then do physics for their job. You go off and work for Astrium, you go off and work for SpaceX, you go off and work for airlines. So just because you are going to go into astronomy or just because you're interested in it doesn't mean you need to become an astronomer. It has sparked that interest. You have asked that question, why does that picture look like that? That is a huge step from just saying, wow, that's cool, and moving on. Okay? And quite frankly, if people don't go into the STEM disciplines, then how on earth are we going to build bridges in the future? Who's going to design the next car? We need people to come into these science, technology, engineering, and mathematics disciplines. And astronomy is a way of attracting people to do that. Helps inform thinking on critical issues, i.e. climate change and the energy crisis. These are two of the political hot topics right now. How do we know about the greenhouse effect? We studied Venus, astronomy. The studies of other planets in our solar system has informed us on how our planet works and how climate change may affect our planet. How can we address the energy crisis? The sun in itself is a nuclear fusion reactor. Nuclear fusion is a great way to solve the energy crisis. So by studying astronomy and understanding nuclear physics, nuclear fusion, you may be able to take your astronomy degree and move into the energy areas and start addressing this energy crisis. There's more. 1/5,000th of a percent of the federal budget, and we are still going. How long have I been doing this? 15 minutes? Easily. All I'm telling you is what you are getting for that 1/5,000th of a percent of the federal budget. Astronomy impacts the classroom and beyond. What do I mean by that? Astronomy has a huge number of conceptual barriers in astronomy. For example, we are on a globe that is spinning, and that globe is spinning around a sun, and that sun is spinning around the center of the galaxy, and that galaxy is moving towards another galaxy, and the whole universe is expanding. Those are huge conceptual issues for somebody who can step outside this room, look around them and go, the Earth is flat. So astronomy has these conceptual barriers that are not very well addressed by standard teaching methods. There are actual astronomy educators that write books on how to teach using innovative methods that engage students and break down conceptual barriers. And by the way, there's over 250,000 undergraduate students that take astronomy each year. That's 10% of the total undergraduate population. Okay? So astronomy can reach a huge amount of people. Strong public outreach. You're at a public outreach event right now, but you are among 60 million people annually that attend these types of lectures or or going up onto observatory roofs later. So we know that astronomy engages people. 60 million people annually attend astronomy events. And this might have been the first one you thought of. Astronomy provides spin-off technologies. Everyone says, the Teflon coating on their saucepan came from the space shuttle. Well, maybe, but X-ray machines are based on X-ray detectors in astronomy. All of this kind of image processing has been led by astronomy. And did you know that the scheduling software on the Hubble Space Telescope has been adapted to give the maximum flow of patients through hospital beds? So astronomy not only provides all of this sparking of the STEM discipline, not only does it engage you guys, not only does it, bring the world together, it only costs us 1/5,000th of the total federal budget. It is a bargain, whatever we spend the money on, as long as it's got the word astronomy in it. It's going to do good. Okay. So before we move on and discuss what may be the big questions for the next 10 years, let's just stop and pause and get a grip on where we are in astronomy right now, where we might not have been, say, 5 or 10 years ago. Right now, we know of over 500 extrasolar planets, planets orbiting around other stars. And here is a direct image of one, orbiting Fomalhaut. This is a NICMOS image from the Hubble Space Telescope. The bright star in the center has been covered by a coronagraph. It's been blocked out. You can see scattered light from the dust in the system. And then over here, you can see a blow-up of the planet moving between 2004 and 2006. So we have direct evidence of extrasolar planets. Black holes are common. Almost every time we look at the center of a galaxy, we find good evidence for there being massive black holes at the centers of galaxies. Black holes, the term black hole in itself is a vernacular. Everybody uses it every day. They put it in titles of programs, in titles of movies. Black holes are common. They are no longer the stuff of science fiction. Right now, we know about the age, the size, and the shape of the universe by studying the residuals from the Big Bang. So this is the cosmic microwave background, the CMB. So from these observations, we now know the age, size, and shape of the universe. That's a big deal, right? We know about dark matter and dark energy. We know that dark energy makes up 79% or thereabout of the total mass energy budget of the universe. And we also know that the universe is expanding, and that expansion is accelerating in itself. So this is where we stand right now. And some people will argue that this is nothing compared to what we are about to see within the next 10 years. All right. So who recommends how we spend this money? Well, I already alluded earlier that it's the entire astronomy community. But there has to be a committee that oversees all that. Okay, so there was this committee for a Decadal Survey, Astronomy and Astrophysics. It was appointed by the National Research Council, which is one of the 4 members of the national academies. This is where things start to become a little dry. So basically, the senior members of the astronomy and astrophysics community were put on this committee, but they solicited input from the entire community in the form of 17 town hall meetings. Many of Florida Tech's astronomy and astrophysics professors went to these town hall meetings. They solicited white papers from the entire astrophysical community. I was involved with 2 white papers to do with the Decadal Survey. So immediately, all of the input into this committee for the Decadal Survey has come from the entire astronomy and astrophysics community. Okay? There were 5 science frontier panels created to figure out what the big questions are. There were 4 program prioritization panels that looked at all of the white papers that were submitted and said yes, that can happen. No, that's a pipe dream. A bit more complicated, but they could look at these programs that were submitted and say, this is more likely than the other one. And then there was also these infrastructure study groups that looked not only at the questions that were being asked, but how to handle the data that was going to be generated or is going to be generated over the next 10 years or so. Okay? So we're looking at what the questions are, whether there are programs that can address these questions and prioritize them, and then how do we deal with everything that's going to be generated from those questions and from the programs. Okay? So the aim of the Decadal Survey, which produced that document that I showed you at the beginning, the New Worlds, New Horizons document, as quoted by Roger Blandford, English. The aim of the Decadal Survey is to optimize the science return for future ground-based and space-based missions in a time of constrained budgets and limited resources. This is quite a powerful statement telling you what care went into this survey. It wasn't just a question of, we think extrasolar planets are cool, let's throw all the money at it no matter what. It was, let's find out what questions we are going to be able to answer given realistic budgetary scenarios and given the risks, technical readiness, and the schedule of the programs that are promising to answer those questions. So it was a very carefully considered document. Okay. So what are these big questions? How did the universe around us form? As you can imagine, they're big questions, right? The cosmic dawn question. How did the first galaxies get there? How did the first stars get there? How did the first black holes get there? So we call this the cosmic dawn question. We are close. We are on the precipice of finding these kind of questions out. We are now back to 13.2 billion years from the WIF-C3 camera on Hubble Space Telescope. So this is the first big cosmic dawn question. The second big question, is there life elsewhere? You know, I could butter that question up by saying, are there habitable planets in Extrasolar? And I do down here, but this is what it basically comes to. Is there life elsewhere? Are we really alone? These are fundamental questions that human society has, and the impacts of the answer will change the world. We are very close to being able to search for habitable Earth-like planets around other stars. Tantalizingly close. And then the third big question, how is the universe governed? What is the basic physics that underlies how the universe has evolved? And it basically comes down to unraveling the mysteries of gravity itself. So these are the three big questions which get referred to as cosmic dawn, new worlds, and physics of the universe. Okay? I think these are pretty important questions. There are some parts of the review that, you know, I don't quite like, but these are, you really cannot argue against these kind of questions. If you can come up with a more fundamental question than these three, then I'm sure there will be a community of people ready to listen to you, as long as you're not, you know, under the influence of something. Okay, so here we go. We've gone through the why we should spend this money, and we've gone through what are the big questions, and we've gone through exactly how much money, well, not exactly, but the kind of dollars that there are available to spend. So the recommendation from the Decadal Survey was split into 5 different areas. And these areas, although they're in a list here, were not really considered independently and separately. They were all considered together. Okay, so one is not more important than the other. You might think that large-scale space-based programs are more important, but they really weren't considered separately from any other of the programs here. Okay? So, the definition, large-scale space-based programs, greater than $1 billion. Good benchmark. $1 billion. On the ground, anything more than $135 million total cost, that's considered a large-scale ground project. Medium-scale space-based projects, between $300 million and $1 billion. Medium-scale ground-based programs. And then finally, an unranked list of small-scale recommended programs. Okay? So this is what essentially came out of the Decadal Survey. So starting with the large space-based programs. These are in priority order, okay? And this is no more important than any of the other areas that I just listed up there. Just because everybody thinks that space is way cooler and spending $1 billion is way cooler, this is considered no more important than the small programs that were recommended, okay? But, nevertheless, you probably want to know what we're going to try and send up into orbit or into orbit around the sun later. WFIRST. WFIRST is an excellent example of how astronomers can tell what an instrument is like without reading what it actually is like. In astronomy, we know that ST stands for either Space Telescope or Survey Telescope. You just know that as an astronomer. IR is always infrared, and WF is always wide field. So before I even read what WFIRST stand for, I knew it was a wide field infrared space telescope or wide field infrared survey telescope. Right? Turns out that it was both. Okay, so the number one priority for the $1 billion in space program is WFIRST. It's a 1.5 meter wide field near infrared imager and low resolution spectrograph, and it's going to answer the questions. Well, it's going to answer all three of the big questions. It's going to be able to address all three of those big questions. So the cosmic dawn, the new worlds, and the physics of the universe. Its cost was assessed to be $1.6 billion, shared between NASA and the Department of Energy, because it is going to look at fundamental physics, high-energy physics. The Department of Energy can get involved. And I said that everything was going to be assessed on a risk basis. This project is considered medium-low risk, because we have all of the technology to launch this very well, with significant ease over some other projects. Okay? So I won't linger on it because it's not as if, everything has an equal importance, right? The second rank was for space-based programs was to augment the Explorer program. So the Explorer program is a bunch of money to basically launch what's known as SMEX and MIDEX and missions of opportunities. So a SMEX is a small Explorer program costing around $160 million. A MIDEX is a medium-scale Explorer program costing around, I think, don't quote me on it, about $300 million. But some examples of these Explorer program science have come from, for example, WMAP, which is responsible for, only figuring out the age, size, and shape of the universe. And then also some gamma-ray telescopes. I think this is SWIFT, and then over here an infrared survey telescope, WISE. Okay, this was assessed as low risk because you get to have a competed program between different, essentially universities saying, I want to have the money to launch my own particular program. This is one of the beauties of the Explorer program, is because it's not dealing with billions of dollars in one lump, huge Hubble Space Telescope project. The dollars can be split down and then essentially farmed out. The work can be farmed out to universities. So one of the great strengths of the Explorer program is that because universities are involved in these programs, students and postdoctoral fellows can get involved, not just high-end scientists in high-ranking positions. Okay? LISA is the laser interferometer space antenna. This is basically going to be put up there to detect gravitational waves. So this instrument is going to be put up there to answer the question of the physics of the universe. Can we detect gravitational waves? The detection of gravitational waves is probably where the next a Nobel Prize will be awarded, because it is going to change the way that we are able to do astronomy. We're no longer going to be just looking at light. We are going to be looking at essentially the warping of space-time. So this kind of LISA itself, if it can detect gravitational waves, which in theory is going to detect an awful lot of, the big problem is not going to be detecting it, it's going to be working out exactly what we're seeing, because you turn it on, you hear the whole universe at the same time in gravitational waves. But this is going to be changing the way that we can actually do astronomy. Okay, it's a partnership with the European Space Agency. It was medium. It was ranked medium in terms of risk, and the U.S. contribution was recommended recommended to be $1.5 billion, okay? This doesn't mean that the money is actually going to be spent. The Decadal Survey is a recommendation to NASA, NSF, and the DOE, right? It's not a you must spend the dollars in the following way. It's we, the astronomy community, politely request that you spend the money in the following way, okay? Moving right along, the fourth rank, IXO. An X-ray observatory that's going to increase our X-ray understanding of the universe by an order of magnitude. There are a couple of X-ray observatories up there right now, XMM, Chandra. They've been doing fantastic work looking at accretion disks around black holes. But because they're fairly early on in the development of X-ray telescopes and X-ray detectors, they're just kind of teasing us with the science that's being able to be done with X-rays, okay? So this was actually ranked medium high, so it got put down at number 4 in the ranked order list of large space-based programs. Moving to the ground, the Large Synoptic Survey Telescope was the first ranked ground-based large project, and we have students and faculty working on this project right now. The fact that this project is fairly well advanced is one of the reasons why it got top ranking. It is a ready-to-go project. So this is going to be able to look at the dark matter, dark energy content of the universe, and it's also, because it's going to be surveying the entire sky every 3 nights, is going to open up a huge window in the time variable universe. So anything that blinks or wobbles is going to be of great interest to this telescope. This telescope is also going to drive a bit of a computer databasing issue. It's going to generate 100 billion megabytes of data available to the public. So, you know, right now you might have a couple of computers on your desk that can handle a terabyte or so. Dealing with that kind of data, it's a problem that is driving other areas, computer science, computer databasing, that kind of thing. Okay, moving on. The second ranked program was the Mid-Scale Innovations Program. It has been recognized by the Decadal Survey that in order to keep astronomy and astrophysics moving forward beyond 2020, we're going to have to invest now to make sure that we are going to have the technology to deal with the questions of the future. Right? It's all very well building a huge telescope on the ground, just seeing what it can do. But at some point, there's going to be a limitation with the technology that we have, the detectors that we have, the adaptive optics systems that we have, that is going to limit the size of the value of any of these telescopes in the first place. So one of the recommendations is to create is kind of augment these mid-scale innovation programs, pump more money into people going, hang on, I think I can adapt the following detector to do the following science. I just need a few $1 million. Okay? So this kind of innovations program is going to keep advancing the forefront of science. That's the idea behind that one. The Giant Segmented Mirror Telescope, third ranked large ground-based program. There are 2 contenders for this one right now. The Giant Magellan Telescope, artist's impression over here, and then the 30-millimeter telescope over here. Okay, this is kind of the build it bigger and we will find something model. Okay, and it's actually why it got ranked as a medium high risk. Right? There's no guarantee that you'll get anything from this, but our experience has shown if you build a big telescope and you've got the adaptive optics to deal with the atmosphere, you'll find something new. And finally, ground-based large-scale programs is looking at basically high-energy tera-electron volt gamma rays and cosmic ray detectors. Okay, so this is opening up the fundamental physics of the universe questions, these kind of things. At the moment, we've got facilities like Veritas down here that are showing that we can do this science. It's like the X-ray observatory, it's like the IXO, right? It's like we need something bigger to continue to look at the high-energy universe. Okay, now we're moving on to the medium-scale programs. The basic recommendation is that one of the big questions is the New Worlds question, but we really don't have the technology quite there to be able to go ahead and detect these extrasolar planets in habitable zones, these exoplanets, these rocky extrasolar planets. Okay, so this program is essentially saying, let's take a breath, let's stop, let's get the technology right before we charge ahead and blast something into space. And the same goes for the inflationary probe technology program. We want to answer these questions of the origin of the universe, but we still don't quite have the technology yet. The detection of inflation, the theory is that during the time of inflation, which is where the universe basically expanded by 10 to the 78 volumes in a ridiculously short amount of time, that it left an imprint on the cosmic microwave background in terms of a pattern in the polarization of the cosmic microwave background. How to detect that is still a bit of an issue. So investing in the technology that's going to allow us to detect those kind of things, is kind of a let's stop, let's take a breath. Let's find out how to do this. Ground-based programs. Well, the ground-based recommendation is for this telescope that used to be called the Cornell Caltech Atacama telescope. It's a millimeter, sub-millimeter, 25-meter telescope, so it's operating on these kind of microwave wavelengths. It's going to potentially answer all three of the big questions, and it's been put at medium risk. It's still called CCAT based on the hill they're going to put it on, actually. CC, yeah. Okay, so the small-scale recommended programs. There are a lot of them. They are unranked, but essentially what they come down to is making sure that we are providing a foundation for new ideas that will stretch into the future. It's all very well coming up with a strategic plan for 10 years, but what happens after that 10 years? If we've just spent all of our effort getting, the following telescope into space or the following 4 projects going, what about after that? We need to make sure that we keep moving forward the forefront of instrumentation, the forefront of our ability to model the astrophysical objects that we are looking at. Okay? So all of these small programs, and I want to point out the definition of a future ultraviolet optical space capability, this bullet point here would be the true replacement for Hubble Space Telescope. Okay? The James Webb Space Telescope is not the Hubble's replacement. James Webb is going to have the same spatial resolution, but this one here, the definition of future Hubble, that gets me excited. And there is money out there to do it, or there's been recommended to be money out there, money put out there to do it. Okay, there are a whole bunch of other conclusions and recommendations from the panel, from the survey, listed here, but this basically comes back to making sure that we have a sensible, sustainable program for the future. Okay, so ensuring the short and long-term future of astronomy and astrophysics. So making sure that we do make international partnerships so that we can get involved in large projects and provide access to larger suites of facilities. Making sure that we do realize that astronomy is embraced and loved by the public. Making sure that we can deal with the data that we get from these facilities that we want to put up there. And making sure that we keep tabs on ourselves, keep track of what we are doing, and making sure we stick to this plan. Okay. So in summary, hopefully I kind of gave you the kind of feeling of excitement that I get about astronomy and astrophysics in the first place. We all love it. You all love it. Otherwise you wouldn't be sitting here listening to me babble on about this stuff. Okay? So we need to embrace that and use that in society. Use that to draw people in to the STEM disciplines. Make sure that the world is going to be able to look after itself in the future. Right? It's all very well, middle managers being able to tell somebody what to do, but if they have no idea how their computer works, what happens when their computer breaks, right? We need people to be inspired. Well, we need to take the people that are inspired by astronomy into the science, technology, engineering, mathematics disciplines and get them to work, to make sure that we don't end up in an idiocracy. Okay? So the big questions, just a reminder, they basically come down to, are we alone? How did the universe begin? And how does the universe work? No big deal, right? The programs or proposed activities have been broken down into space-based larger medium, ground-based larger medium, and space and ground-based small. What a mouthful. But there is no one area that is considered more important than the other. Okay? The top-ranked programs were, as we just went through, WFIRST, Augmenting the Explorer program, the Gravitational Wave Observatory, the X-ray Observatory, the Large Synaptic Survey Telescope, this Innovations program to make sure we've got the opportunity to keep moving forward, a giant, let's see what you've got out there, 30-meter telescope, this high-energy telescope, investing in the technology we need to answer these new worlds and these origin and cosmic dawn questions. What was this one? Oh, yes, the sub-millimeter and millimeter telescope, and then making sure that we keep moving forward by giving us a solid foundation for future ideas. Okay, so that's hopefully all I've got to say on that. Thank you.